As we begin this section, we first need to review a little bit about exponents. So whenever a smaller scale number is written in the upper right corner of another digit, that's exponent. So for instance, 10 to the first power means multiply 10 by itself one time, so it's just 10. 10 cubed, 10 times itself 3 times. And if we verify this in our calculator, we will get that as 1,000. And then 10 to the 0 is just the value 1. And indeed, any number to the 0 power is always equal to 1. So if we see 5 to the 0, we know that's another way to write 1, as is 3 to the 0. For any non-zero number to the 0th power as an exponent, then the overall value is 1. If we were going to calculate 7 to the 4th, it would be 7 times 7 times 7 times 7. We can verify this in our calculator to be 2,401. Another exponent rule to be aware of is that for any number b, so b is just a variable to represent any value, b raised to the exponent 1, so b to the first power, is always going to just be the value b. So for that reason, if we had 3.256 to the first power, the value would be 3.256, as would be 1,001 to the first power, the value is just 1,001. Now with these exponents, we saw in a previous section how you can write out our numbers into what could be called expanded form. Or that's what we're going to learn here today. So this is expanded form. This represents the digit. If we just check in our calculator and simplify each step, 10 to the 0 is 1, so this is 1 times 1, plus 10 to the first power is 10, so that's 8 times 10, plus 10 squared is 100. You can verify this in your calculator. 10 times 10 is 100, that we are multiplying by 5, plus 10 cubed is 1,000. We were multiplying that by 2, plus this is 10,000, that we were multiplying by 3. Calculating each of this, we would get for the first term, this gives us 3,000, that we're adding to 2,000, that we're adding to 500, that we add to 80, that we add to 1. Adding these all together, we would get the value 30,000 or 32,581. Now this is what is called expanded notation, and we're going to use this not only in this section, but it's going to be pivotal for our next section. So I highly recommend reviewing the expanded notation. So if we wanted to write 3,250 or 32,581 in expanded notation, we would do so in this format. And what it's doing is it's breaking down exactly how many of each. We might think of these as our building blocks of our number system. How many ones do you need? How many tens do you need? How many hundreds, 1,000s, 10,000s, and this could continue if it was a larger number with how many 100,000s. For the next example, we're going to do something similar. We want to take this expanded notation and determine what value of a number it represents. So I recommend you pause the video and work through similar as we did here and unpause to check your work. I know 10 to the 0 is 1, so this simplifies to 3 times 1, or you could more simply just write it as 3 all of a sudden. 10 to the first power is 10, that we're multiplying by 0, so this would contribute 0 from this term. 10 squared is 100, we are multiplying it by 4, plus 1,000, we are multiplying that by 0 from above, plus 10,000, that we are multiplying by 2, and then 10 to the 5th is 100,000, that we are multiplying by 9. Simplifying this term by term, we get 900,000, plus 20,000. Now 0 times 1,000 is 0, so we're adding 0 there. 4 times 100 is 400. 0 times 10 is 0, plus 3, which would simplify to 920,403. So this is an example where we went to from expanded notation to our number system, how we generally write it, in base 10. And what's going on here is we're going to learn later about the idea of base 10 numeration, and we are just expressing exactly how this breaks down in base 10 as a number. In this example, we're going to go in the opposite direction. Now we have a number expressed in our normal number system that we've been working with, and we want to break it down into the individual pieces in our base 10 system. The way I recommend doing this is thinking about it, this is the ones, the tens, and the hundreds place. So we could simplify this to say that we have 7 times 100 to represent the 700. We would express this as the 56th part, so we have 5 times 10 to get us to 50, and then we're adding 6 times 1. And then to simplify this just in terms of the base, later on we're going to use it in this way. We want to be able to take this 1, 10, and 100 and express it as powers of 10 to show it through the expanded form of the base. So if we're talking about base 10, then we would express 1 as 10 to the 0, that we multiply by 6, plus now 10 just by itself is 10 to the first power, that we were multiplying by 5. 100 is 10 squared, that we were multiplying by 7. So this would be the number fully written in expanded form, and if you like, you could add parentheses just to make it clear that these are grouping together. Both are equivalent. And the pattern here is we have our ones written to the farthest right. That's the 10 to the 0. And then notice as we move to the left, the exponent increases by 1 each time. So at first we're talking about ones, and then tens, and then hundreds through the 10 squared. For this next example, I recommend you pause the video, write it out in expanded form. It might help you to think about how would you even express this number in words. That will help you break it down into the individual components, and then unpause to check your work. This can be broken apart into 4,560 and 8. And then we would want to express this in terms of the base 10, so the increasing powers of 10, which would be written as this. In this next example, we would express this as 46,478. So we might first write it as 4 times 10,000. That gets us to the 40,000. And then we have a 6,478 that we're adding to 40,000, so that would be 6 times 1,000 plus 4 times 100 plus 7 times 10 plus 8 times 1. And then we know we can rewrite 1, 10, 100, 1,000, 10,000. These are all powers of 10. Specifically, this is 4 times 10 to the 4th plus 6 times 10 cubed plus 4 times 10 squared plus 7 times 10 to the first power. And then we know 1 is just 10 to the 0 power, so this is plus 8 times 10 to the 0 power. In some future examples, we are going to be adding and subtracting in this expanded form, kind of breaking down why we have the concept of borrowing and carrying over if we are just doing addition and subtraction on our paper. And to do that, we need to think of the idea of kind of regrouping terms of the same base. So we're going to review the distributive property. Let's first look at this example, and then we'll look about how it looks like in an abstract format. If we have 3 times 10 cubed, we know this is 3 times 1,000. 10 cubed is 1,000, plus 5 times 10 cubed, which is 5 times 1,000. And the key here is it's 3 times 1,000 plus 5 times 1,000. We are adding similar measurements. So 3 1,000s plus 5 1,000s would be the same as 8 1,000s. And this is the idea of the distributive property. What's going on here is you can imagine that you're factoring out the 1,000. So we have 3 plus 5 that we're adding together, and then we're multiplying by 1,000, and that's where we get the 8,000 as the result. And the key thing to notice whenever you want to use this property is you need to have 3 times 1,000 plus 5 times 1,000. We are adding the same types of things. If instead we were looking at 3 times 10 to the 4th plus 5 times 10 cubed, of course this could be simplified into 3 times 10,000 plus 5 times 1,000, which is equal to 35,000. But not in the same way. We had to break these apart, and these were not measuring the same amounts. 3 10,000s is measuring a very different type of quantity than 5 1,000s. Abstractly, what this might look like is if we've got b times a plus c times a, then we can rewrite this as add the b and the c together, and then multiply it by the common factor of a. And in this essence, we have factored out the a from both terms, simplified this expression first, and then multiplied. Now we're asked to use expanded notation to add 23 and 64. Let's just add these as we would have normally done first, and then we'll see what we mean by expanded notation. We've learned in previous classes how to add two numbers. You would line them up, so you would have all of them what we might call right justified. You line up the last numbers to the right first, and then in this case they both have 2 digits, but if they weren't, then there might be extra digits here, and you just add each item. So we know these represent the ones. 4 ones plus 3 ones equals 7 ones. 6 tens plus 2 tens is 8 tens, and we would get the answer 87. But this is not expanded notation. To add things in expanded notation, we first want to break down what do these numbers represent. 6 and then a 4 in our number system means 6 times 10, because it's 60 plus 4 ones, plus 4 ones, okay, which we know we could write as 4 times 1 is 4 times 10 to the 0, 6 times 10 is 6 times 10 to the first power, and we were adding this to 23, which is 2 tens, so 2 10 to the first powers plus 3 ones, so 3 times 10 to the 0 power. And then we think of our idea of what we just saw with the factoring or the regrouping property from before with the distributive property. You can add like terms because we're adding these. So the 10 to the 0 powers can be thought to add together, as can the 10 to the 1 powers. So let's do these piece at a time. If we have 4 times 10 to the 0, and we're adding that to 3 times 10 to the 0, it's like we've got 4 of something plus 3 of something. That would give us 7 of that thing, plus 6 of something plus 2 of something would give us 8 of that thing. And this is where we know we would get the value 8 times 10 plus 7 times 1 would give us 87. So in this case, this is expanded notation because we first wrote the numbers that we were adding in expanded notation themselves and then added the terms together. And what we've learned since elementary school is just the shorthand notation of this, because at one point we got so comfortable seeing 6 and then 4 written in this order to know that that was 60 plus 4. Next, we're asked to use expanded notation to subtract 342 from 987. So first, we need to know the order here. If we're subtracting this from this, then we have the 987 comes first. With subtraction, order matters. But we are taking away 342 from this amount, so then we say we're subtracting 342. Now, this is not expanded notation, but we might do this first just to guide our thinking, and then we would write the numbers out in expanded format and group the like terms. So 7 minus 2 is 5. Now 8 minus 4 here is 4, but what this is representing is there's 40 in difference here. There was 5 ones, and then 40 as the digit 40. And then we've got 900 minus 300 represented by this 9 minus 3 in this third position. That means there's a difference of 600. Now to do this in expanded notation, I recommend you first pause the video and then write out this subtraction symbol in expanded notation. So instead of 987, write 9 times 100 plus 8 times 10 plus 7 times 1 and so on, and then unpause to check your work. So written in expanded form, we would have this, and then we subtract like terms. So we subtract first the ones from each other. So 7 times 10 to the 0 is 7 times 1 minus 2 times 1. That would leave us with 5 ones. Okay. And then if we subtract the next group, 8 times 10 to the 1 minus 4 times 10 to the 1, that would leave us with 4 times 10 to the 1. Okay. And then 9 times 10 squared, so 900 minus 300 would give us 600, or 6 times 10 squared, written in a different way. This would be the subtraction in expanded notation. And as we should expect, we would get the same answer whether we did our subtraction the same way that we've been doing since elementary school or in this expanded notation, because it is the same idea. This is just a more efficient way to do the subtraction in expanded notation. So this is more efficient, but they are doing the exact same idea. Just to get some intuition as we've normally done that, and then we'll think about how to do so in expanded notation. Now 5 plus 8 is going to be 13, but I can't write a 13 here because we know the first digit to the right of all the numbers represent the ones, and 13 isn't a measurement of ones, it's 110 plus 3 ones. So what we do is, this is the ones place, and then we do what's called carrying another digit. So 13 could be expressed as 3 ones plus 110. So by adding this extra 1 here, we are increasing the digit amount by 10 to represent for the 13. So now we have 10 plus 70 plus 40, which would add up to the digit 120. Or as we might have done in our previous way of thinking about it, we would say 7 plus 1 plus 4 is 12. But by the positional numeration, we know this is 100 plus 200 plus 3 in the ones. 100 plus 20 plus 3, which could combine to be 120 plus 3. So this is why we have the idea of carrying as we work through these number systems. Let's see how that looks whenever we're working with expanded notation. Now, as we're adding these together, we could write this here as 5 plus 8 is 13 ones. Now we're going to have to change this eventually because whenever we express the amount in the ones position, it needs to be a value 9 or less, but we can leave it as this for now, plus 11 times 10. But again, both of these are getting multiplied by a base value of 10, but it's larger than 9. So we need to do what's called a regrouping. So let's rewrite these as 13 is the same as 10 plus 3, that we are multiplying by the base 1, plus 11 is 10 plus 1, that we are multiplying by 10 to the 1. And we will multiply these out, so by the distributive property of multiplication across addition, these go to each of these pieces. So we'd have 10 times 10 to the 1 plus 1 times 10 to the 1 plus 10 times 10 to the 0 plus 3 times 10 to the 0. And each of these two can be further simplified. So 10 times 10 to the 0, if we think about in terms of adding exponents, 10 is in exponent form 10 to the first, and whenever the same base is getting multiplied together, the exponents add. So you could think of this as simplifying to 10 to the first 1 plus 0, which would just be 10 to the 10 to the first. And you can also verify this in your calculator, or you could think about it, 10 times 1 is just 10. Now 10 times 10 is 100, which we also know is 10 squared, or you could think about this 10 as 10 to the first and add the exponents together to get 10 squared. So we could rewrite this by regrouping, and we would get this. And now whenever we just have 10 squared, remember multiplying by 1 doesn't change the value, so we could express this as 1 times 10 squared to show we've got exactly 1 of the 10 squared units. Plus, again here, 10 to the first could be expressed as 1 times 10 to the first because that doesn't change its value. And then what we notice is these two have something in common. We've got 1 times 10 to the first, so we've got 1 times 10, which is 10, plus another 10. That could be simplified as adding the two ones, and we've got 2 10 to the first powers, plus 3 10 to the 0 power, plus 1 10 squared, and we can see this is exactly 123, just in expanded notation. So whenever we're adding things in expanded form, in order to get down to the proper format where we are multiplying by the powers of 10 digits 9 or less, we had to expand this out, as we did here, and then we had to simplify like terms to get to our final answer in expanded form. And we did the exact same idea that is encompassed in this idea of carrying the 1. So for these problems, you can always check your work by adding them or subtracting them based on how the problem's worded in the traditional way, and verifying that against the expanded form of the method. For our next example, we do need to correct this word here. We need to use expanded notation to subtract 186 from 364. Now, based on this wording, we know that 186 is coming from the 364. So let's just do this as we normally would to get some intuition, and then we'll do this in expanded notation. Whenever we try to take 6 ones away from 4 ones, we realize that we don't have enough ones to do that. Okay? If we are taking 6 ones away from 4 ones, we see that we have a -2 left from the top. So what we're going to do is instead we're going to borrow. So this is going to decrease. Instead of a 6 here, it's going to become a 5. But remember what that represents is, since the 5 is in the second position of this digit, that's really now 50. But if we just leave this as 354, then we've changed the value of the number. What we need to do is we then bring the 1 that we decreased it by, which we really are decreasing it by 10, and we write that in front here. So this is like saying 350 plus 14, which we know is still 364, so we're keeping the value the same. So this is the idea of borrowing the 1, and now we're going to think about it as this. What is 14 ones minus 6 ones? That would give us exactly 8 ones. Okay. And then here we think about this 5 minus 8. But what's really going on here is we've got 50 and we're subtracting 80. We can't do that because we can't take away 50 from 80 without going negative. So the technique is you then borrow from the next place over. So you decrease this to 2, but what that's really representing now is 200, right? But we can't change the value, so you then add a 1 here, plus 15, since it's in the second position, is multiplied by 10, plus 14, which is still 364. So this rewriting is not changing the value at all. It's just allowing us to actually think of the subtraction. Now 15 minus 8 would give us 7, which represents the idea that we've got 70. So 150 minus 80 is 70. 2 minus 1 is 1, or we can think of this as representing 200 minus 100 is 100, since it's in the third position of the number. And we get our answer is 178. Now this technique of taking from a higher base over is the idea of borrowing. And let's see how this would look in expanded notation. So to begin, we're just going to express this subtraction in expanded notation. So 3 times 10 squared is 300, plus 6 times 10 to the first would be our 60, plus 4 times 10 to 0 would be the digit 4. And we are subtracting 1 times 10 squared, plus 8 times 10 to the first, plus 6 times 10 to the 0. And that should have been a 0 there, 2. And as we think of subtracting these like terms, we see that we want to subtract 6 ones from the 4 ones, 8 tens from the 6 tens, and then we want to subtract 1 100 from the 300. We're going to start at the lowest terms first. We can't take away 6 ones from the 4 ones because there's not enough ones there to subtract from. So we do the idea of borrowing. We rewrite this as now 5 times 10. But what we did is we took away a 10 and we gave it to the ones position. So instead of 4, we now have 10 plus 4 or 14. So we would see this as our 8 times 10 to the 0. Now 5 times 10, 50, minus 80. We can't do that yet. We need to have a larger value at the top. So we borrow here. But whenever we're taking away from the 3, we're actually taking away a 100. So we're taking a 100 from this place, but to keep the number the same, we then give it here, which we express as 15, because 15, at first we had 5 times 10, which is 50. But whenever we have 15 times 10, that's 150. So you can see that we added that 100 to this place. That would leave us with 7 times 10 to the first. 2 times 100, so 200 minus 100 would leave us exactly 100. So we get the exact same answer before, but maybe in this case the borrowing can be a little clearer of why whenever we just cross this out and write a 5, we then put a 1 here, because we're borrowing the base and moving it over to the smaller form of the base so that we can actually subtract. So that's it for this video. Be sure to message me on Canvas if you have any questions, and then do the textbook homework and then the section quiz from this section. Thank you.